In this presentation, we'll be talking about the basics of ARM assembly language. I, Paul, will cover briefly ARM memory, register operands, as well as the basic ARM instruction formats. Yasmina will be explaining some important instructions in ARM, and finally, Rakan will illustrate these instructions with some examples. ARM memory. ARM uses byte memory addresses. Each instruction is 32-bit wide. Addresses of consecutive instructions differ by 4. Memory locations are addressable in different size chunks. They could be 8-bit, 16-bit, 32, or 64 bits. The 8-bit is considered as bytes, 16 as shorts, 32 as words, and 64 as longs or doubles. Also, when addressing memory, ARM uses a 26-bit address value, and most instructions are one word. ARM register operands. ARM has 16 32-bit register file, R0 to R15. We have 13 general-purpose registers and 3 specific-purpose registers. R0 to R12 are general and R13 to R15 are specific. R13 is a stack pointer, R14 link register, and R15 is a program counter. To operate on a variable in memory, we first load the value from memory into a register, we then perform the instruction, and finally store the result back into memory. Going to and from memory could be very expensive, so it's better to keep variables in registers. Basic ARM instruction formats. We can identify two formats. We have R-type and I-type. And each instruction in ARM should be encoded in 32 bits. In the R format of ARM, we can identify 3 types of registers. We have 2 source registers Rn and Rm and 1 destination register Rd. We can as well identify the opcode, the operation code, which is similar to MIPS. And we have some examples here, and is 0000, sub 0010. We can take an example, add register R0, register R1, and register R3. This could be encoded as, we replace add by its opcode, which is 0100, R0 by 0000, R1 by 1, and R3 by 3, and we finally convert to hexadecimal representation. Here in the I format, we can identify 2 registers only. We have the source register Rn and the destination register Rd. We have also the opcode, the operation code, and in addition to the R format, we have an immediate constant value, and we have shift, which corresponds to a right rotation. We took an example here, RSB, R7, R10, and number 49, and we converted this instruction to binary representation and finally to hexadecimal representation. In this slide, we want to represent a constant with shift and immediate 8. We have a certain formula to find this value, and this formula contains shift right, shift left, and a bitwise OR. For example, if you want to represent 1920, we represent first of all shift with the number 13, immediate 8 with 30, and we apply the formula above to get the final value, which is 1920, and the same applies to 256.
We will focus on the most important instructions in ARM, like move, left shifts, right shifts and arithmetic right shifts, load and store, and branching. The syntax of move instruction is move RDN, where RD is the destination register we want to save the value on, and N is a 32-bit immediate integer value, or it can be a register containing a value. As we see, R5 is equal to 5 and R7 is equal to 8. When we write move R7, R5, this means that R7 takes the value of R5, so R7 becomes equal to 5 and loses its initial value 8. We have to note that ARM is not case sensitive, so the registers can be written as uppercase or lowercase r. Left shifts effectively multiply the content of a register by 2 to the power s, where s is the shift amount. As an example, consider this instruction, move R0, R0, LSL7. This means that the value of R0 is multiplied by 2 to the power 7 and stored in register R0. As we see, R0 was 7, and after the shift to the left, it changed to 896. We also note that shifts can also be applied to the second operand of any data processing instruction. As an example, consider add R1, R1, R0, LSL7. This means that the value of R0 is multiplied by 2 to the power 7 and added to R1. The resulted value is stored in R1. Right shifts behave like dividing the contents of a register by 2 to the power s, where s is the shift amount, if you assume the contents of the register are unsigned. As an example, consider move R0, R0, LSR2. R0 was before 1024 and after the shift to the right and adding 2 zeros to the left, R0 became 256. On the other hand, arithmetic right shifts behave like dividing the contents of a register by 2 to the power s, assuming the contents of the register are signed. As an example, consider move R0, R0, ASR2. R0 was before minus 1024 and after the shift to the right and adding 2 ones to the left, R0 became minus 256. LDR is used to load something from memory into a register. It is written as LDR, RA, RB between brackets. LDR operation loads the value at the address found in RB to the destination register RA. STR is used to store something from a register to a memory address. It is written as STR, RA, RB between brackets. STR stores the value found in RA to the memory address found in RB. ARM's load and store instructions are versatile. They provide a wide range of addressing modes. Here are some of them. LDR, RD, RN 12 between brackets means that RD is loaded with the contents of memory at the address found by adding the contents of the base register to the supplied constant. When we write LDR R2 R3 without any number, this means that the offset is assumed to be 0. As we see in the third instruction, offsets can be either added or subtracted as indicated by a negative sign. What's special in ARM is that the offset can be a register and can be positive or negative as shown in the fourth and the fifth instruction. And what's more interesting in ARM is that register offsets can also be optionally shifted. As we see, consider the instruction str r4 r5 r4 lsl2. This means that the offset is equal to r4 multiplied by 2 to the power 2. A branch is an instruction in a computer program that causes a computer to begin executing a different instruction sequence and thus deviate from its default behavior of executing instructions in order. There are three types of branching instructions. Branch B. Its syntax is B-label. It is basically a simple jump to a function called label. Branch link. Its syntax is BL-label. It saves the program counter in the link register R14 and jumps to a function called label. R14 is a special register in ARM that is used to hold the return address for a function call. Branch exchange. Its syntax is BX-RM, where RM is a register. This instruction is used for branching like B and BL. What differs is that they are used for instruction mode change. The two modes are thumb and ARM mode. Thumb mode is a 16-bit memory and ARM mode is a 32-bit memory. The last bit of the register RM determines which mode it is.
So we're going to do an example of our assembly code. We're going to translate the C++ code into assembly, which is sum equals to 0. So we're initializing the sum to 0, and then we're doing a for loop from I equals to 0 to 10. And with each incrementation, we're adding I to the sum. So The first step in the assembly is let's assume R1 is I and R0 is the sum. So we initialize their values to 0 each, and then we open the loop. In the loop, we add R0 and R1 to give the new R0, which is the new sum, and we add 1 to I to give an incrementation to I, and then we compare R1 by 10. If R1 is less than 10, we go into the BLE loop as it satisfies the condition, and if it's greater than 10, we halt the program and the program stops. So we're going to go over another example. This one showcases the load and stores in the assembly language. So the C code is we're creating a list of 10 integers, and we're initializing the sum to be equals to 0, and we're going over a for loop for I between 0 and 10, where we're incrementing the sum by the value of the object in the list of index I. So its code in assembly is dot align 4, which gives each number like 4 bits, and the list x, which is dot space 40. So 40 over 4 is 10. So we're giving the list a size of 10, and we go over the sum. So we give R0, move it to equals to x, which is the base of x, and we move R1 to be the sum. So LDR R2 comma R1, we load the value of the sum into R2, and we set R3 to be equals to 0, which is the one we're using to initialize I. So we go over the for loop. LDR R4 comma R0 R3 LSL2. So we're adding R0 to R3 LSL2. LSL2 basically means we're shifting the R3 value 4 bits to the right. So we're adding R0 to the next value in the list. So we add R2 and R4, we give back R2, which is the sum, and we increment I, which is R3 by 1. So we compare I with 10. If I is less than 10, we continue, we branch back to 4, and if R3 is greater than 10, we shift the right R2, so the iteration ends and the list is complete as it is.